Hi, I'm Radha Maturi and I'm presenting our paper on the rise of machine learning in beamforming. We have built an automated framework that maps research at the intersection of any two technical fields. Although we are demonstrating this with AI and beamforming, the approach applies to any pair of cross-disciplinary fields. The topics to be covered are key concepts, introduction, methodology, findings. Beamforming is electromagnetic beam steering, a complex problem where multiple AI approaches claim effectiveness. Our question is, which is best? Research question: does AI improve beamforming? And if so, how? Our analysis required a systematic literature review to identify AI claims. Introduction: the problem is rapid growth in publications and overwhelming manual review methods. Our approach transforms literature analysis from exhausting archaeology into systematic science automation. Challenge of scale: we are enabling new types of analysis that reveal invisible insights. How do we analyze the explosion of research happening at the intersection of two advancing domains of knowledge? This chart reveals the scale of the challenge. Three papers in 2015 growing to 535 papers a decade later. We need automated approaches to literature analysis. With 210% annual growth, traditional review methods are impossible. One person cannot comprehend this volume of rapidly evolving research. Our platform makes this process orders of magnitude faster. This is our approach. We construct a set of queries to research dual domains. Our scope can include the title, abstract, or even the entire document. Terms are combined using typical Boolean expressions. The final analysis returned 509 papers common to both domains. This transforms search and review from art to science. Our development followed a three-stage process. We started with archive.tar that gave us the first analysis of cross-field papers. Archive Group focused on finding all method subtypes across the literature. Archive Odin performed the Cartesian product analysis, examining every possible combination of the techniques. Contrast: traditional approach: a researcher with a stack of 500 papers spent 6 months trying to make sense of a huge literature landscape. Sound familiar? Compare that to this approach. The same 500 papers analyzed in minutes, revealing patterns no human could spot manually. Going from months to minutes is transformative. It makes the process deterministic instead of random. Researchers can spend their time on analysis rather than archaeology. Consider breadth and depth. We are analyzing 500 papers spanning 17 years, a complete evolution of two fields in 6 minutes instead of 6 months. This chart reveals the growth of two different domains and their intersection. Consider the green area, that's beamforming and machine learning intersection. The problem isn't just the number of papers, it's the acceleration. The methodology rests on two pillars, which are tag sets and cosine similarity function. Tag sets distinguish categories from specific algorithms. Tag sets consist of two things: coarse high-level categories indicating what, fine low-level algorithms indicating how. Cosine similarity finds semantic relationships that keyword matching misses, identifies related concepts in papers that don't share keywords, captures connections that traditional search methods miss. Example: adaptive antenna arrays and smart beamforming share concepts despite different terms. We looked at tags and cosine similarity. What is their combined impact? Enables mapping of technical relationships, provides insights when different terms describe similar concepts, reveals hidden connections in cross-domain literature. Separation of concerns. Here it is: what we know versus how we figured it out. This simple phrase captures the core insight of our analytical framework. What we know represents the domain knowledge. How we figured it out represents the methodological knowledge. Most literature conflates these two dimensions. By keeping these concerns separate, we can ask better questions. This separation transforms messy cross-field literature into actionable intelligence. There are two kinds of tags: coarse and fine. We abbreviate tags for plots. This slide shows 6 core tags for machine learning. There were 107 fine tags for machine learning, but this was reduced to 98 for clarity. This slide shows 8 core tags for beamforming. This slide shows the first 10 of 30 fine beamforming tags. This slide shows the framework for a dual domain classification system. We have 8 cores categories on the machine learning side and 11 on the beamforming side for a total of 88 combinations. Similarly, we have 32 fine algorithms on the machine learning side and 17 on the beamforming side, yielding 544 combinations. This slide shows the evolution of our tags. Tags were added and refined as we gained experience. Here is a summary of our approach. Separation of concerns. Course categories capture strategic paradigms. Fine categories detail algorithmic implementations. Tagging system. Automated identification of algorithm usage across literature, reduce bias, and scales objectively. Cartesian product examination. Automated analysis maps every possible beamforming machine learning tag combination. Identification of emergent versus saturated areas. Detection of research trends and gaps reveal underexplored opportunities. The components of our platform are as follows. Automated archive mining, knowledge extraction through a server-friendly approach. TF-IDF factorization plus cosine similarity analysis enables relationship detection beyond keyword matching. Temporal detection algorithms identify patterns, trends, and trajectories. Interactive engine enables exploration from course categories to specific algorithms. Our findings provide two insights: emergent versus saturated areas, gaps in research. This chart tells industry what technology to bet on. MIMO dominance. 58 papers, that is 62%, demonstrate MIMO ML integration. Paradigm diversity. 5 beamforming approaches benefit from machine learning enhancement. Hidden opportunity. Adaptive beamforming shows only 16 papers, that is 3%, despite being the best ML fit. Hybrid potential. 40 papers or 7% combine analog efficiency with digital flexibility. These findings guide future investment opportunities. ML adoption reveals clear patterns. Supervised learning dominance. Deep learning leads with 115 papers, followed by attention with 38 papers. 8 of the top 15 techniques require labeled training data. Unsupervised RL. Q-learning with 78 papers leads policy gradient methods with only 18. Future trajectory. The field transitions from label-dependent methods to unsupervised approaches. This analysis maps every course beamforming by machine learning combination, revealing strategic patterns. Hotspot. Massive MIMO by supervised deep learning leads with 23 papers. Systematic gaps. Blank cells aren't empty spaces, they are untapped opportunities. Strategic insight. The matrix reveals focus on proven combinations, leaving opportunity for new approaches. This category treasure map suggests strategic directions towards unexplored intersections. This analysis maps every fine beamforming by machine learning combination, revealing three things: sparse coverage. Only 25% of ML enhanced beamforming techniques are explored. Prioritized opportunities. Three blue gaps represent high value targets. Data driven planning. Stop guessing what to research next. Use data to find the best opportunities. Lopsided singleton analysis reveals the following gaps. We found gaps in the degree of adoption of specific ML algorithms. Consider beamforming precoding. Some of the biggest missed opportunities are here. Instead of finding successful combinations that already exist, we note missing combinations that should exist. Headroom. It appears from the graph that plenty of headroom exists for machine learning integration. Machine learning techniques not used for beamforming. Deep learning has a 99 paper gap. RL has a 74 paper gap. Transfer learning has a 10 paper gap. Reinforcement learning works for interactive problems but is rarely used in wireless beamforming. Transfer learning isn't used for beamforming, even though new base stations could learn from existing ones. The wireless field hasn't examined all that ML has to offer. Here are our conclusions. We analyzed 548 papers in minutes versus months, orders of magnitude faster. We identified techniques rarely paired in both domains. We used cosine similarity to find connections beyond keyword matching. We created a course versus find classification tags. We used separation of concerns. We performed knowledge extraction with intelligent rate limiting. Literature review now become a deterministic reproducible process. Data-driven priorities replace ad hoc research directions. The resulting maps enhance decision making and communication.